Dobrodošli u Naučni klub Centra za promociju nauke. Večeras je ovdje sa nama profesor Kit Devlin sa Univerziteta Stенфорд iz USA ili iz Sjedinjenih Američkih Država. Profesor Devlin je jedan od najpoznatijih svetskih matematičara i popularizatora matematike i večeras će nam pričati o matematici u 21. veku. Now we will continue in English. Professor Devlin, please come, the stage is yours.
I learned up to the age of 21 when I got a degree in mathematics became irrelevant during my own lifetime. Everything I spent all of that time learning how to do can be done on this device faster, with accuracy, much more accuracy than I have. I struggle with equations that have 2 or 3 or 4 variables. You can give this one 100 variables, 1,000 variables. In a fraction of a second, it will give you the exact answer. Not just arithmetic, algebra, calculus, differential equations. It will do everything, and it's free. It's in the cloud. I have not gone out of work. I do more work for the government and for companies than at any time. We still need lots of mathematicians, but we don't do what we used to do. The way mathematics is done in the world is totally different from the way it used to be done. I'm looking around this audience. There are some people my age, some people not quite as old as me. There are very few young people. So your experience learning mathematics was the same as mine. But if you have children, they will go out to live in a world where mathematics is no longer done that way. It's totally changed. And the poor school teachers are faced with trying to change to meet the needs of the 21st century. I'm going to be talking about mathematics in the 21st century. Another way of looking at it is it's mathematics, that's better, mathematics for the 21st century. Okay, the cameraman is not very happy because the lights have gone down. So it's mathematics in the 21st century from an educational perspective. It's mathematics for the 21st century. Okay, in order to explain what's happened and why it's happened and how it's done these days, and I will give some examples of the way mathematicians, one exception, in the university mathematics departments, mathematics is mostly done the way it was done 2,000 or 3,000 years ago. Mathematics has been done the same way for thousands of years. In the mathematics departments, it's almost unchanged, not totally, but almost totally unchanged. There are some parts of mathematics have changed a lot. But outside of the university mathematics department, in the engineering department, in the physics department, at Google, at Amazon, at Walmart, at any of the large companies, any of the large corporations, FedEx, UPS, all around the world, the way mathematics is done is totally different from the way it was done 200 years ago. And from the point of view of people, it's really good because mathematics used to be restricted to a small number of people who learned how to do all kinds of calculations. Now, almost anyone can do the mathematics the way it's done. And I'll talk about that later. I've actually worked with high school classes, and in 3 or 4 days, I've got them to the point on their own where they can solve major problems that industry uses all the time in just 5 or 6 hours. Things have changed so hugely, it's really quite staggering. And as I say, teachers are having a lot of trouble around the world adapting to this new way of teaching that matches the new way mathematics is done. Okay, let's just think about how mathematics is done in the world. Throughout history, mathematics has been developed and used to solve real-world problems. One of the early branches of mathematics, geometry, was done to map out the land, in particular in the Nile Delta. Every year it flooded, and when it flooded, they had to redraw the boundaries of people's land, and so they invented a technique which eventually got the Greek name geometros, geometry, for earth measurement, for mapping it out. Very practical purposes. Trigonometry, where you take geometry and you measure angles, that was largely for navigation, finding your way around the world, etc., etc., etc. So you begin with some real-world situation, and then typically you do something like this. Let me give you an example. Supposing you wanted to build a house. You have some land, you want to build a house. You talk with your family, and you come up with ideas of what you want the house to look like. You then go to an architect who will talk with you, and that architect will take your description of your house and describe it in a technical language. So your ideas, which will be how you want it to look, the kind of things you want to do with it, how you want the rooms, and the architect will do an architect's description. It will be a different language. The architect will express it in different ways. The architect will then go to a draftsperson who is going to draw up the actual plans. Or they may do it themselves, but someone eventually will draw plans, and plans are essentially mathematical descriptions. There are charts, there are schematics, you see rectangles, you see angles written in them, there are maybe some spreadsheets associated with it. All of this will become very precise, and a blueprint for a house is like a trigonometric drawing. So it's now become a mathematical description. So it has two translations: your meaning, architect's description, then the blueprints. Once you've got the blueprints and it's all written in sort of an explicit language, then the person can go and do mathematics. They can do all the calculations: how much timber, how much cement, how many bricks, all of the calculations, the costings, the times. They will give you an estimate of the bill, and you can then decide whether to go ahead. Using the fact that it's been expressed in mathematical language, you can do all of the calculations in advance to figure out exactly how you're going to do it, how much materials you want, and so forth. When you've done that, you hire crews that come in and actually build the house. And that takes you back to the real world. So you've gone from the house to the architect, to the blueprint descriptions, to the calculations, and then to coming in and building the house. And throughout history, every time mathematics has been applied in the world, it's been in that cycle. That is the basic way we apply mathematics. I'll give one more example other than building a house, because in the case of building a house, it's not surprising that mathematics is used, because houses look like rectangles and so forth, as it's clear. What about if you tried to use mathematics to study people? Well, here's an example. A few years ago, but I should just mention before I go on, this part of it over here is generally known as a mathematical model. It's purely done by mathematics. None of this is done on your plot of land. That's done in an office or a coffee shop or somewhere with people doing mathematics. And that's the area that I worked in for the early parts of my career. I spent the first 20 years of my career doing that kind of stuff. Someone would give me some mathematics and then I would work on the mathematical problem. Okay, let's go away from that. So a few years ago, I worked in the United States. I worked on a TV crime series called Numbers. Came out of Hollywood, 2003 or 4 or something. It was a huge success in the United States. It got 12 million viewers. Went on to 5 seasons. I worked on it for the first 3 seasons as an advisor. And this was about how you could use mathematics to solve crimes. And the plot was as follows. There were 2 people that were the main characters. The guy on the right was an FBI agent, and the guy on the left was his younger brother, who was a young math professor at Caltech in California. They didn't call it Caltech, but it was actually filmed at Caltech. And every single episode, and this went on for 5 seasons, every single episode followed this plot. That's me, and the guy on the left is the star, and that's me next to him. It's a little bit hard to see with the lighting, but that's David Krumholtz, who was the star. He actually became the most well-known mathematician in the United States, but he actually never graduated in mathematics from high school. So we used to joke about that. Okay, every episode had this sequence. You began with a crime, and the police would come in with a crime. It's a serious crime, so they would call in the FBI. And the FBI agent comes in, and he starts to work on it, and first thing he does is he gets all of the statements, he gets the details, he turns it into police language. He writes a report, etc. So it's now been translated from a crime scene, which is full of blood and all sorts of things. Now it's the police description, and then you see him trying to solve it, and he gets stuck. And so he asks his younger brother, Charlie, he'd say, help me out on this one. So Charlie would come in and would talk to his brother, and he would translate the problem from police language to mathematical language. He would then go away and do some mathematics. And the fun thing was, you saw him do the mathematics on the television screen, and it was all correct mathematics. I and various other mathematicians made sure that was correct mathematics. So all the mathematics you see is correct. You saw him do it. He would then present the results on a board or a computer screen to the FBI. They would talk about what to do next. and then they would take those results and they would go and catch the criminal. Every episode for 5 years followed that. That's the mathematical cycle. One of the interesting things when this began, the first episode was screened, some of the critics in the newspapers said, this is unbelievable. You couldn't use mathematics to solve serious crimes. Well, the first few episodes of the entire series were all true. They were real crimes and they were used real cases, and what we saw was real. After the first few episodes, they ran out of cases that made good television, and so they had to invent cases, but in all of the times they did that, they talked with me and other mathematicians to make sure the mathematics was correct. So this was absolutely true. In fact, the very first episode, which was about a serial killer in Los Angeles, was based on a real case in, I think it was Louisville, Kentucky, of a serial killer. And that guy there is the real FBI mathematician person who solved that case. He was one of the pioneers in using mathematics to find serial killers. His name is Kim Rossmo. He was a police officer that went to university, did a PhD in social science and in with mathematics. And he actually developed a formula. This is his formula. It was used to solve real crimes using a technique that became known as criminal geographic profiling. What that does is when you've got a serial killer or a serial rapist or something, if you've got serial cases, and you need 5 or 6 cases before you have enough data, but if you have 5 or 6 or more cases and you use this formula, it will tell you where the criminal is most likely to live. And you can draw a map, and again the resolution is, we're missing there's a lot of washout here, but on the image, if I could see it, you can probably just make it out vaguely, that's a contour map. There's an area where the criminal's most likely to live. It's in yellow in this thing, then orange, a bit further out, then down to greens and blues. It's a contour map of where the criminal's most likely to live. And so you would fit, at that point, the police officers go into the hot zone, the part where the person's likely to be, and they just look for DNA samples. And they get enough DNA samples until they can figure out who it is. That's how it worked in the first case, and it worked out in other cases. So you can use mathematics to solve crimes. That means you're going to use mathematics to look at the way people behave. It's not just the planets. It's not just spacecraft. You can do it with people. With the planets, you get an exact answer. You know exactly where Mars is going to be a year from now. We can make very accurate predictions with the planets. We can tell where that Tesla's going to be in the future, the one that went up there a few weeks ago. You can tell where things are going to be in physics. In the case of crimes, you can't say exactly, but you can increase the chances of finding the criminal. And an awful lot of mathematics today, in fact the vast majority of applications of mathematics outside of the universities, it's not about finding exact answers. The real world almost never has exact answers. It's about finding better answers, better solutions, more efficient solutions, safer solutions. We can't eliminate deaths on the roads, but using mathematics we can reduce deaths on the road, etc., etc. So, in the world we now live, the kind of mathematics that's been done is absolutely crucial, and there's a huge need for people to do that kind of mathematics. Let me go back now and talk a little bit more about geometry, the one I mentioned a few moments ago. To most of you, that's geometry. It was certainly, that's what I thought geometry was when I went to school and when I graduated from high school. Then when I got to university, I learned that there were other geometries. In fact, there were many other geometries. In fact, there were so many of them that you have to say, well, that's just a very interesting special case that was important 2,500 years ago. Because geometry is about shape. But shapes all over in our world. Some shapes we can see. Some shapes we can hear. Some shapes we can only follow in our minds. There are many, many shapes in our minds, and I'm going to give some examples. In fact, the most interesting ones where mathematics is powerful is not the shapes you can see, but the shapes you experience in your life. With geometry, with modern geometries, you can study the shapes that we experience and that we do not see. We see them with our minds and we see them with our experience. So triangles are good, they're fun, they're really useful to begin to learn about mathematics because they're very simple. The shapes we experience are not quite as simple, but they're not that much more complicated in many cases. So in today's world, there are many more relevant shapes. And this is where mathematics becomes very powerful. It reveals invisible patterns. With mathematics, you can look at patterns and you can even represent them on a page, even though they're invisible to the eyes. You can make them visible. Mathematics, I wrote a book some years ago called The Language of Mathematics, subtitled Making the Invisible Visible. Interestingly, I thought that was my title. I thought I'd come up with that. I thought it was very clever. And then I was watching a TV documentary about art, about an artist in, I think it was somewhere in the United States. And on camera, she said, artists make the invisible visible. And I thought to myself, I thought two things. I thought, this is really cool. I said that as a mathematician, and she said that as an artist. And then I thought, maybe I'd read about her, and I'd got the idea from her. And then I thought, maybe she'd read about me and got the idea from me. Either way, we were both being accurate. And so I'm going to begin in a minute with an example of an artistic use of geometry to make the invisible visible. And the question is this: in today's world, in many places, and I'm going to be looking at New York City, in New York City you have people living in a geographic space. They're living in a Euclidean geometry. But their experience is not, because we have many cultures, many languages, many traditions, people of very different kinds, all living in the same geometry. Can we use geometry to look not just at the way people are geographically located, but how they're interacting culturally, socially, linguistically, etc., etc.? And the answer is, yes, we can.
So we got China, Chinatown over there, China there, Little Italy there, Vietnam and Singapore down there. The whole world is collapsed in upon itself. This is the space we're living in. This is my neighborhood right here. This is my neighborhood. I love it.
"500 years ago, painters first used geometry to give perspective to the city of Florence. In New York City, another artist uses geometry to give a different kind of perspective to his world."
I think the main vehicle that artists use to communicate emotion is space. You could say the history of art is the history of different spaces. And these spaces are an embodiment of the mathematics of the time, of the geometry of the time. What four-dimensional geometry can do is give you a model of the complexity of the world that we live in. It was as though I could plunge my hands through the computer screen and handle this four-dimensional cube like quicksilver changing and turning inside out. For days, I dreamed only of these images rotating and turning inside out and behaving in these very mysterious and yet recognizable ways. The problem for the artist who wants to make art about space is to make space itself present, make space itself visible. This may appear to be diamonds, but I can rotate them to reveal that behind the diamond really a whole three-dimensional cell was hidden. They can be turned again in the fourth dimension to reveal that they really were sections of hypercubes. For 30,000 years, human beings have made patterns. It's some fundamental way that we have to organize and structure our experience. Making patterns can be the ideal way to define space. The plotter draws.
This is about 20 years old we made this video. You can do this on any laptop now.
And
then it was cutting edge.
I can use this as a study for a larger painting. To make a larger painting, I photograph these drawings and project it with a slide projector onto a larger screen where I can replicate what the plotter does. Each slide is its own complete three-dimensional space, and many slides make many different spaces in the same place at the same time. And these three-dimensional spaces can interpenetrate one another and can interweave and can overlap each other in paradoxical ways. It's the idea of having mastery over complexity. What the fourth dimension means is being in many spaces at the same time, or having many separate spaces superimposed and yet remaining distinct. I think we have a misunderstanding about seeing. We think we see the world out there with our eyes, and that this process is objective and automatic. In fact, we see with our minds. We go through life doing geometry. You know, Plato said that the gods are always doing geometry. We're always doing geometry. We go through life applying the geometry that we know on our visual world. And if it doesn't fit that geometry, we don't see it.
Layering four-dimensional shadows on a two-dimensional canvas, Tony Robbin explores new ways to link the spaces we imagine to the spaces that we live in.
Okay, so that was part of a TV series called Life by the Numbers, which I worked on way back in the late 1990s, so it's kind of old. Most of the segments, it was 6 hours of it. There was 6-week series for an hour each week. And most of the things in the episodes, there were 10-minute segments. Almost all of them, there's no point in looking at them because mathematics changed and changed and changed. So things that were cutting edge 25 years ago are no longer interesting. This was before Google discovered how you can look at the shape of connections and do geometry of connections on the internet and find the right information very quickly. And Google is really a geometric algorithm. So this was way back before any of that. This particular episode is still very valid. It was valid in Plato's time, as he talks about. It's an incredibly powerful way of looking at things. It's still Euclidean geometry. These are triangles and rectangles and cubes and hypercubes. It's just Euclidean geometry in 4 dimensions. But that extra dimension allows you to look at the complexity of multicultural, multisocial, multilinguistic, multiracial living in the same geometric space, the same Euclidean space. So they're both Euclidean geometry. The one on the left was cutting edge when the world looked like that, because that's all about triangles and rectangles. The modern world isn't. There are triangles rectal, and the modern world is very different. And so you can take Euclidean geometry, and just by going one dimension higher, you can do things about the real world. Now you may say, okay, but that's just art. And it is art, it was an art gallery. But if history tells us anything, it's if you want to see what scientists will be doing a year from now, look at the present artists, because art is always in advance of science, either in the case of visual art, or science fiction, or even just ordinary fiction programs. Art is always there first, because that's what artists do, right? They reflect on society, and they reflect on the way society is going. So by looking at this, you will see how we think things will be going. And he was doing this work 20 years ago, when he had to use those tools. It was only later that the real mathematicians and scientists started to do that kind of thing. But it's not just art. Incidentally, the other people that we have to look to if we want to see what's going to happen tomorrow are the philosophers. In science, there are two groups of people that scientists talk with a lot when things are changing. There's the philosophers and there's the artists, because that's what they do. And if you want to design technologies that fit well into society, you talk with artists. There was a reason why the Macintosh became very, very big. It's because Steve Jobs talked with artists and people who designed fonts and yada, yada, yada. Okay, if that still doesn't convince you, how about an application of geometry that saves lives and fights terrorism? There's one. This is one I worked on. That was a tool that I didn't build, I just specified it. I was called in for a project some years ago with the US Army, and they were interested, they wanted to, you know, this was in the fighting terror. That's an aerial map of part of Baghdad. And this was a unit that was, actually the unit I was working for, their job was to design missions which would minimize loss of life, minimize the life of the troops, minimize the life of the civilians living all around. They were trying to develop surgical capabilities to kill people that were going to kill other people, but to do it without killing other people. So that needed mathematical precision. And what they wanted to do was have a tool that allowed them to see invisible things that couldn't be seen from a satellite view. Now, as we all know from the movies, the NSA and the CIA, they can get aerial views that can go down to sort of, you know, a few feet. They can, I mean, this was just a high one. They could zoom down. They could see all of the stuff in the Euclidean geometry. What they couldn't see was all of the messages being passed secretly. I mean, they could listen to the messages on cell phones, but they couldn't see all of the other stuff. There was a lot of connections between things on the ground. And so what they wanted was a way of visualizing all the invisible connections through messages being passed, signals being sent, people who knew people, networks. They wanted to be able to visualize all of the invisible stuff. And so I worked on a project to come up with a geometry that helped them to do it. And the reason they asked me is I'd written 3 books over the years which had described how you can do that. How you can do what Tony Robbins did in the art gallery, and how you could do that for real to build technologies. And based on what I was doing here, and this was actually developed to make companies more efficient. I wrote a book with a Croatian mathematician, a Croatian social scientist living in the United Kingdom, Duška Rosenberg. She was an interesting person. She began in social linguistics, ethnography. She was a social scientist. Then she went to the UK, well, she went to the UK to study, then moved to the UK, married a guy called Rosenberg, and she then did a PhD in computer science, and she became expert in understanding how communication gets in the way in the workplace and making it more efficient. And then she and I started to collaborate, and we developed ways of visualizing communication in the workplace. One of the examples we looked at many times was air traffic control. We would get the transcripts from airplane disasters, and then we would look at the transcripts and we'd say, can we visualize the communications geometrically so that you can see where things went wrong? You could just see, you've got a picture, and you say, wow, that was when they made the decision that eventually caused the plane to crash. And we worked on that, we came up with methods for doing that, dynamic methods for doing that. And so based on that, I was actually asked to sort of do the same thing for the army. And the last thing I did on the project, I was not part of the I mean, my job as a consultant was to come up with a geometry. So the very last day when I made my presentation, and this is page 9 of my presentation, and it was only about 8 slides, I said, okay, here's how you might want to implement it. You have the commander has a screen, and on the screen, this is all live. There's the interactive map that you can zoom in, you can move it around, you can rotate it, you can look at it from street view, you can do all of that in that map. And they already had that capability way back. This was back in the early 2000 period, I think. So they had all of that in it. But behind the scenes, that was linked to all of the objects in this geometry. Now, it doesn't matter what these things are. These are geometric objects. They're the equivalents of those hypercubes in Tony Robbins' work. But there's many of them, and they're nested, and they're connected. So there's connections between them. And the idea was that the person controlling the mission would reason in here, and when they wanted to know about something else, they would go over to here, and they'd reason with those, they'd move them around, they'd look at the connections. So you had 2 eyes. You had the visual eye on the actual scene, and you had an eye on all of the hidden connections. So it was making visible all of those hidden connections. I have no idea if this has been used. I had no security clearance. I didn't have access. I gave them my deck and wrote up a paper, and off they went. But that's not the art gallery. That's fighting terrorism, and it's keeping people alive. And it's accepting the fact that some people are going to be killed. But given that fact, let's try to minimize the ones. It was working on projects like that that made me think a lot about being a mathematician. Because I realized the moment as a child I decided to become a mathematician, I was doing something that could be used to kill people. And that's kind of worrying. But it is the world we live in, sadly. And having recognized that, I thought the least I could do is try to use that mathematics to minimize the loss of innocent lives. But it is the case, and it was just true for Archimedes. Archimedes developed war systems. You cannot do mathematics without doing something that can save lives and can take lives away. It's just the way the world is. Okay, go back to this. That's the last black thing. I'm going to end, the talk will end on one of the most upbeat messages you've ever heard. I'm going to end this talk with something that makes me so excited and so pleased to be a mathematician, you won't believe it. It's unbelievable what we can do these days. And we can actually prove mathematically that there's real hope for humanity. And that's not something I thought we'd see in my lifetime. Okay, so that's that picture, the one about the mathematical modelling. Okay, how does that get played out? In real term, how do people do that? Here, step by step, is how that process is used. You identify some pattern in the world. In that case, it was the hidden communication going on in a battlefield. The stuff that people are trying to keep secret. Identify a particular pattern in the world. You study it. I studied it. In fact, in those books I wrote, the one with Dushka Rosenberg, we studied communication patterns for months and months and months. And we developed notations to talk about them. We actually ended up developing that particular little diagram that I talked about. So you develop notations to do it. This is the specialized language. This is the middle of the top line, the real world situation. Then you go to the next one, you develop notations and so forth. And the reason she came and asked me to help her is she realized that she needed to go over to the right-hand side. She did the middle bit. She said, I need this in mathematics. It's too complex. I can't get the answers. I've got so much data, and it's so hard to make sense of it. I need some precision from mathematics. So she actually came and convinced me to work with her. So my job was to provide the right hand, to take it over to mathematics. Because once you've done that, you can start studying it using the tools of mathematics. And then you can even start writing down basic axioms, like Euclid did with geometry, that describe exactly what you're going to do. And this is important because at some point, you're going to apply that mathematics to something you don't fully understand. You'd better be confident that you've done the mathematical model correctly, because it's going to give you answers. And if you have started it off on the wrong footing, it's going to give you answers that are the wrong answers, and it could be incredibly disastrous. So writing down axioms and being careful at this stage is crucial. But once you've done it, then you have a tool that can be used all the time. Okay, so you study that abstracted pattern and you prove things from the axioms, which means that whenever you've got an application where the patterns meet these axioms, you can use any result you've derived. So you've now got a body of knowledge that can be used as a toolbox to answer questions. And you can actually develop procedures that other people can use. I mean, the one that most people meet that's really significant in the modern world is calculus. You can apply calculus to anything that moves in a continuous fashion. Planets or aircraft or cars on the roads or money in a currency system, water flowing down pipes, all of those kind of things. You can study music using the tools of calculus. And you can just use the procedures. And as we all know, it's possible to learn, first of all, we can learn how to do arithmetic, Hindu Arabic arithmetic, 10 numerables, units, decimals, 100 columns. We learn the rules as children for doing arithmetic, and once you've learnt them, you don't need to think about them. It just works reliably all the time, and you don't even need to fully understand it. Almost no one who learns calculus understands it at first, but they learn how to do it. And later on, some people learn how to understand it, and it's important that they do, but most people don't. Okay. The point is, when you've got the rules and procedures, anyone can use them. And when you've done that, we apply it to the world. So now we've got all of the steps that take you around that triangle. This part is what I worked on for the first 20 years of my career. That's the mathematical part. I spent 20 years, I didn't care where the problems came from. I just liked doing mathematics. I liked solving problems. I was attracted by the beauty, and that's what I did. And it was only later on in my career, as an accident, unintentional, that I stumbled into this other world and discovered that the particular kind of things I'd been working in turned out to be very important in the model world. So my mathematics went from being irrelevant to being at the center of a lot of activities, including intelligence, defense intelligence analysis, video analysis, all sorts of stuff. And the world just changed. And I just by chance found myself in the middle of that world. Otherwise, I would be giving you a different talk tonight. Okay. Or maybe no talk, because you might never have heard of me if I'd done that. But just the way it went. I didn't change, the world changed. Okay. So this is what I spent the first 20 years doing. It's what's still done in the mathematics departments. Axioms, proofs, the mathematics departments in the high schools and universities, and procedures. In fact, in the school system, that's mainstream mathematics. In the school system, that's the focus. And there's a good reason why that's the focus. It's almost the exclusive reason in the schools. It's getting less so, and it will continue to get less so. But it was the main focus for 2,500 years. Because until you could do that stuff, you couldn't do anything else. Until we had computer systems and apps and various other tools to do other things for us, the only way you could do this was if you mastered that. So you had to spend the first 15, 20 years of your life learning how to do that. In fact, when I grew up, unless you were good at arithmetic, you couldn't even go into a shop and buy anything if you didn't want to get someone to make a mistake. You had to do the calculations in your head to buy things. So you couldn't even do everyday life without mastering basic arithmetic. And you couldn't do much anything else. And you certainly couldn't do this kind of analysis without that. So there's a good reason why for thousands of years that was what mathematics education was about. But just as my life changed because the world changed, that's true now for all math teachers. Which means today's math teachers have the excitement and or the misfortune of it being more difficult for them than at any time in human history. And it is difficult. In the colleges and universities, you look at all of those. But in a university mathematics department, that's all you look at. Engineering department, other things. Physics department, other things. Biology department, other things. But in the mathematics department, that is still the main focus. Which is just as well, because that is absolutely important that people do that. But it's now a speciality. What used to be essential for everybody is now just a speciality for a very small number of people who enjoy doing it. And for everybody else who didn't enjoy doing it, the good news is you never need to do it again, because we have other ways of doing it now. Okay, so using that method, by the mathematical method, I mean all of those steps, identify a pattern, develop a notation, study it, all of that. How do we do it in the 21st century when we've got that iPhone in our pocket that can do all of the procedures? Well, most of the problems in the world, in fact, I might as well say all the problems in the world, other than a very small number of weird exceptions, don't have simple solutions. They have hundreds or thousands of variables. There is no right answer. There's better answers, worse answers, acceptable answers, dangerous answers. But the world is complex. Answers is a different kind of thing. It's never a case of proving something in the world. It's a case of convincing yourself and convincing other people, which is a matter of getting information. So what mathematics is used for today isn't to answer questions. It's to get information so that people can answer questions. The people are in the driving seat, individual people or societies, but they need information. They need good data. That's what mathematics is used for today, to get good data, to get better data. And it requires a big picture approach. And for the most part, cloud resources, which you can access on a smartphone, they do in American English, do the math, the procedures, the equations, the formulas, the differentiation, the integration, all of the stuff, differential equations, etc., inversion of matrices. All of that is done instantly, correctly, by tools that are freely available. What we need to know is how to use those tools. I mean, these are not simple tools. These are sophisticated tools, and using them requires a lot of sophistication. Some years ago, when I was doing all of this work, I and other people, this was by no means just me, but we all at the same time started using this phrase, mathematical thinking, to talk about doing mathematics in the new world. And I use the word mathematical thinking to distinguish it from doing mathematics in the sense that we all grew to know it. So it's not doing the formulas and the equations and the calculations. Those are all done by machines. It's the thinking part, which is the stuff that machines certainly are not even close to being able to do now. Okay. So it is worth mentioning, at the same time as people started talking about mathematical thinking, over in computer science, computer scientists started talking about computational thinking, because there came a point around the same time when you no longer wrote computer programs. People stopped writing code. They started assembling code. They found code that did jobs, and they found ways to knit code together to do something. True story. One of my close friends is a guy called Peter Norvig. He's the chief scientist at Google. And he got that job. I mean, when Google was founded, he was in his early 40s, which was very old for Google. You know, that was when Brin and Page were in their mid-20s, so getting towards 30. So, but they hired Peter Norvig very early on because he was known as being one of the world's best computer programmers. And he now is in charge of all of the research at Google. And he will tell you, and he's told me, and I think he probably says this on video somewhere, he doesn't understand how the young programmers write programs. They do it in a very different way. It's not the way I learned how to write programs. It's not the way he used to write programs. The young people, I have a video game company, and I design learning video games, and we have on staff a full-time person who writes code, who's a very good game developer. I have no idea how he does it. In fact, we have difficulty talking because I try to say what I want and he doesn't see the world the same way. He writes really good code and it works. I have no idea. And if I look at his code, I have no idea how it works. He's just pulling stuff together and I can't follow it. If he leaves, we're in trouble because no one can understand the code. Actually, he's a really good programmer. He annotates. So we're not in danger. Good programmers annotate, so you can go in and fix the code when they've left. Okay, we wouldn't have him doing it if he didn't do that. Okay, so let's fade that stuff out, because that's the stuff that's been done by machines. The actual formulation, no, the people do that bit. But once you've got them, once you've got the axioms and things, The rest of it sort of is out of the way. We do sometimes do it. But when we look at that level of detail, it's because we want to understand the tool to make sure it's going to do what we want to do. You have to be able to go in and look at how things work. So it's faded away into the background. It hasn't gone away, and occasionally we do some of that, but not much. And the way I describe that is that most mathematical problems now, you don't need a mathematician to solve them, but you ought to have one mathematician on the team. And there are plenty of people, and that's what I've been doing for all these other things, with the various jobs. I am just a mathematician on the team, and most of the time I'm not needed. I'm only needed when it comes to these points of view, these particular points. So you need a mathematician on the team, but you don't need them very often. You know, I can go off and ride my mountain bike for a few days, and the cell phone will ring, and I'll go and answer a question. Okay. We almost never prove theorems. It's not about proving theorems. It's important that some people do, and that's what happens in the Department of Mathematics at the university. And there are many people who'd like to do that. There are many more people who'd like to do that than can find jobs doing that. And it's extremely competitive. So maybe one of your students in 4 or 5 years at the high school will get a job doing that. But the rest of them, if they're mathematically able, will not be able to find a job where they can do that. But they can find a job doing mathematics all the time, because there's an incredible shortage of people who can use mathematics to solve problems in the real world. And they're very exciting problems, and they're interesting to work on. Yeah, I was lucky because I lived at a time of transition, so I was able to spend 20 years doing the first thing and then the rest of my career doing something else. Okay, most of the time, that's done by technologies. If you find you need to solve an equation, invert a matrix, whatever it is, anything procedural, anything that can be done by code is done by code. And there's a particular tool that became available a few years ago, I can't remember, it's 10, 15 years ago, whatever it is, a thing called Wolfram Alpha. It's free. There is a free version on the cloud. You can do it on your smartphone, although you really need a bit more real estate because most equations are more complicated. But this tool is really simple to use, and it does all the mathematics for you, right through the most complicated stuff in undergraduate mathematics. And it does it instantly, correctly, fraction of a second, any amount of data. Give it simultaneous linear equations in 50 unknowns, 1,000 unknowns. It'll give you the answer. I'm going to use it in an example in a minute. Okay, so all of that's done by tools. I mentioned Wolfram Alpha because it's one of the first things that we turn to because it's so simple and it's available, but there are many others. This is my list of tools that I use if I'm working on a problem, in the order of importance. If I've got a new problem, the first thing I do is just go onto Google and I type in the keywords for my problem, because the chances are pretty high that somebody else in the world has already solved it. Don't need me. Just go and find their solution. Sometimes, when I go into Google, I see a reference to something I don't understand, a term I don't understand, a technical term, you know, some kind of an equation or something. I just go into Wikipedia, because in mathematics, the answers on Wikipedia are almost always correct, and they're always up to date. So you can get the latest information on something in mathematics almost always on Wikipedia. So that's my second tool. At that point, I probably need to send an email to someone to check something. Maybe I've seen the name of someone and I want to find something. So I'll send an email to someone and say, yeah, I see you did some work on this. Can you sort of send me some information or give me some ideas? So the next thing I do is email. Then I go to Wolfram Alpha, because I can do things very fast and get a sense. By then, I've probably seen the reference to some mathematical method that I'm not familiar with. So I go into YouTube and I type that thing on, you know, maybe linear programming, for example. I might find a reference to linear programming and think, what's that? I sort of think, maybe I heard about that as an undergraduate. And I go onto YouTube and I'll type in linear programming, and for that example, you'll get hundreds of videos of people giving 15, 20-minute lectures explaining linear programming. So you look at a couple of videos and you think, oh yeah, that's right. And because of the way the ranking works, the ones that come up first are usually the best. So very quickly you get someone who's very good at explaining linear programming, whatever it is. By now, I've probably reached the stage I want to play with the numbers to get a sense of how big a problem is it. So I'll get a spreadsheet out, put some figures in a spreadsheet, or download some data from a website in comma-separated variable form, import it into a spreadsheet, write a few macros that I've picked up from doing this, run some experiments, and without spending any money and much time, get a sense of whether this is a big problem. What kind of answers come out? Just what are the numbers like? Then it gets a little bit more detailed. I might want some more specialized tool like MATLAB or something else to just find out some more, to learn some more about it at a deeper level. Because I've been in the business a long time, I have a very good LinkedIn network, and so I can use my LinkedIn network to find my way to experts and get information from the world experts. There's a resource called Math Overflow, which the name comes from the computer scientist Stack Overflow, which if you've got a technical math question, you go onto Math Overflow, you type it in, and usually within 10 minutes, somebody in the world, somewhere, gives you an answer. So you're crowdsourcing the entire world, and the answers you get are usually pretty good. They're usually very good, so that's a good resource. Then I might want to use something very specialized like Mathematica, which is an expert's tool for doing all kinds of things. It's sort of, in some senses, it's behind Wolfram Alpha, but Wolfram Alpha does a lot of other things. And then maybe I'll use Quora, because that's a way of sort of getting more detailed answers and sort of more philosophical answers. I'll just put a question on Quora, and you get, I mean, I actually have never put a question on Quora, but I often look on there and get ideas, and people do that one all the time. I mean, I've put it near the end because I've never actually used it to do that job. I do actually use Twitter quite a lot because I've got about 12,500 followers, many of whom are professional mathematicians. And so I can simply ask a little question in 140 or whatever it is, 280 characters now, and some mathematician in the world will just reply to me. And if you look through my Twitter feed, you'll see that very occasionally. And then there's one more tool, because sooner or later, I have to use the oldest tool that we have for doing mathematics. That hasn't gone away. You're going to need paper and pencil. The machine is not going to solve it. It's going to provide all you need, but eventually, if you don't need that, then the company or whoever it is, they don't really need you. You can just tell them, I've done a search, here's the tools, go and buy that product from these people and they'll tailor it to you. But the mathematician's important when you actually have to say, well, that gets me close. Now I'm going to have to do something else. So at the end of the day, you still need to do that. So that's still one of the tools. It's not that mathematics has gone away, it's just changed because there's all of this other stuff. And it was just in time, because we're doing this because modern problems are complicated. They're complicated because the world is complicated. But that complicated world has given us all of these tools to deal with its own complexity. So it feels complicated to people of our generation because it seemed much simpler. But it doesn't seem very complicated. You know, I was in a high school down about 200 kilometers to the south earlier today, and we went in the robotics lab. And the high school students were building robot systems that could find their way around. And these are high school students doing what Google is doing with self-driving cars on a tabletop. And they were getting these things built out of Lego, and they were working. They were following streets, they were turning left, turning right. And you can do that at high school. The world has just changed. Those kids didn't find it complicated. I chatted briefly with them. They didn't find it complicated. They found it the most natural thing in the world. So to us older folks, we recognize the complexity because it's different from what it was. But to younger people, they've grown up with that complexity. When I published this chart a few months ago in an online column I write, and I got two kinds of responses. People wrote comments and saying, yeah, that's how I do it. And other people saying, I have no idea what you're talking about. How can a mathematician use any of those? It's an interesting transition. Okay, let's move on. I've told you what mathematical thinking is. I've told you what the tools are. what's it really look like? What do you do? What do you actually do? What's going on in your head when you do mathematical thinking? How do today's pros do mathematical thinking? They do it the same way today's computer programmers write computer programs. They use heuristics. Let me go back one. Heuristics. And because that's a fairly obscure English term, and you may not know the English term, there's probably a Serbian term for it. Well, it's not originally English, of course. It's Greek, so maybe it exists in Serbian. But in any case, that's the Wikipedia definition, and I'll underline or highlight the key phrase. Practical method, not guaranteed to be optimal or perfect, but sufficient for the immediate goals. That is how we do it. We use making mistakes as a tool. You try something, you get it wrong, you think about why it's wrong, you try it again, and you just follow your intuitions. You develop sophisticated skills of reasoning. And I'm going to give you an example now. And this is the one math question you're going to have to solve here, in your heads. And we're going to give an example. I'm about to put up a problem. It's a very simple little puzzle about buying something. I'm going to give you some information about buying something. The moment you see the problem, I want you to answer it to yourself. You don't have to write it down, but just answer it to yourself as quickly as you can. It's not about whether you get it right. It's about what you learn about how your brain works when you try to solve a problem. Because if we as humans can figure out what kind of mathematics our brain is really good at, then with all of those tools, we can all do mathematics. And I actually saw the kids in the robotics lab doing exactly that with the computer science analog. So this is a very simple problem, and when we've done it, and as I say, I want you to just answer it immediately. And then we'll look at what you did. And you don't have to tell anybody what your answer is. Are you ready? And you have to do it quickly. A bat and a ball costs $1.10. The bat costs $1 more than the ball. How much did the ball cost on its own? It's not a trick question. It's a simple arithmetic question. You've had enough time. You've probably come up with an answer. I'm sure you've come up with an answer because you're human beings. Okay. Here's by far the most common answer. By far the most common answer. And I'll call this solution 1. You say, you see that word more, costs more, and you say to yourself, this is about subtraction. If you thought that, strike 1. You're smart. You recognized it as a subtraction. Computers would have trouble with that, even if you had good parsing. But human beings say, it's about more. This is subtraction. Step 2, you said, what numbers can I subtract? There's only 2 numbers. You've got 2 pieces of data, $1.10 and $1. And your brain instantly went into subtract $1 from $1.10. And you come up with 10 cents. You don't have to put your hand up and whatever, but statistically about 58% or more will have got 10 cents. And you were absolutely smart for getting 10 cents. This is not technically a trick question, but it's a question that's designed where the method that works most of the time and is super, super smart actually goes wrong. It's a heuristic you used. If you said it's about subtraction because it costs more, and you said I've only got 2 numbers, and you subtract one from the other, that is an absolutely smart thing to do. It's very fast, and it almost always works, and it's a human thing to do. You recognize the pre-important words, you did the smart things. But this question was phrased in a way where that's wrong, even though it's the smartest thing. There's another way you could do it, which is solution 2, which is use the method you've probably learnt in the schools. It's an unknown, so let x be the cost of the bat. At this point, people think, oh, x, no, because algebra isn't human-friendly. Algebra is very unnatural. Let y be the cost of the ball. So human beings have every right to feel weird when they see algebra. Algebra was invented in the 9th century around Baghdad because trading was getting more important, and Baghdad was a centre of trading, and they were doing lots of calculations all the time, and they realised they were doing the same calculation again and again and again with slightly different numbers. And so they said to themselves, and they were smart, we need to be more efficient at doing these calculations. Instead of doing them as arithmetic, we'll use x's and y's and we'll work out rules for x's and y's. And yes, you'll need some paper or you'll need a board to do it. You'll need to write it down. But at least you don't have to go through the whole process with new numbers. You just have formulas you can apply. Which was fine, but it meant you had to turn yourself into a creature that deals with fine details. And the human mind is terrible at dealing with fine details. We're good at recognizing things instantly, like, oh, it's a subtraction problem. I've got to subtract this number from that number. So if you feel nervous about algebra, good, because that's the human response. And you never need to worry anymore because you can pull out your iPhone and it will do it for you. So then you have x plus y is $1.10. We know that it's $1 more, x is $1 more than y, so x is y plus 1. So you can eliminate the x, and you get $1.10 minus y equals y plus 1. You can bring the y over to one side. You get 0.1 is 2y, so y equals 5 cents. And that's the right answer. That's not a heuristic. That's not even human. That's a technique that was developed because people were trying to be more efficient in the 9th century when they had no devices to calculate with. It's a procedure. You have to learn the rules. It takes some time to learn the rules. It's very slow. You have to write things down, unless, I mean, very few people can do it. I actually, because I spent years doing this, I can do that one in my head. But if there's 3 variables, I can't. It's slow, but it always works. And the other thing I haven't written down is any high school kid could actually write a computer program to do that. I mean, they wouldn't. They would just pull one off GitHub. But you could do that. Okay, so that's lesson 2. What about solution 3? And this is the solution that most professional mathematicians do. And I actually was first met this problem. Someone asked me this question. And exactly the way I've asked you, they said, do the question. And I actually very instantly gave the right answer. And I didn't do that. I used the fact that I've been a mathematician for many years and I'd developed what we call number sense. I just visualized what it was about. And it turns out that this is the way essentially most mathematicians do it. The actual way to visualize it isn't true. But here's what goes on with someone who's become they've acquired number sense. If you Google number sense, you'll get definitions of number sense. And it's a big, big deal in mathematics education these days, because it's what you need to focus on. You say to yourself, there's a cost of a ball that we're trying to find, and we don't know what it is. You know, how much is the ball on its own? So there's this thing called the cost of the ball. So in my mind, I had, okay, there's this unknown thing. And since it's a cost, I sort of thought about it as some sort of a rectangle. I mean, this is just trying to put it into a diagram. I had this sense of this thing called the cost. And then there's the bat and the ball, and I formed an instant image. I was just as quick as this. It's just using a different heuristic. I had a picture in my mind of the bat, because the bat was like the ball plus something else. It was the ball plus something. Same sentence, I just got different information from it, just as quickly as you did if you did solution 1. So if you did solution 1, you were doing exactly what I did as a professional, but I'd developed a different set of heuristics through experience, so I just saw that instantly. I didn't look for problem type, I looked for a type to do with numbers. There were 2 number types, there's one that's 1 more than the other. And then we use the fact that the bat plus the ball is $1.10. So those 3 bits, cost, ball, cost, and bat, the extra bit, those 3 bits together add to 110. So I didn't calculate, I just read off from that mental diagram the fact that the ball is 5 cents. If all of these bits together is $1.10, and that's $1, that's 5 cents, and that's 5 cents. I didn't calculate that. I just saw it, because that's number sense. How did I get number sense? Do mathematics for a long time. Interesting. That's a heuristic. It's fast. And this one always works. Because if you can go beyond the words and the symbols to what they mean, if you can develop a sense of numbers, you don't have to do any calculation, you just read it off. This is a good heuristic if you're at school, because at school it was about solving problems. And the fastest way to solve a problem was say, is it a subtraction problem? Is it a multiplication problem? And those of us that passed our exams quickly, we developed those heuristics. Unfortunately, and that was useful, I made a good career, been good at doing that. I've worked as a mathematician for years, but then Wolfram Alpha came out, and suddenly that skill was completely irrelevant. But Wolfram Alpha can't do anything like that. No computer can do that. Humans can do that. That's what it's all about. And so we have to get the next generation of kids over to the right-hand side. Historically, the only way to get there was to start with this, forget that, learn a lot of that, and then learn that. Because unless you learned that, there was no way you'd get over there. What we don't know yet is how much of this you have to do in order to get there. You certainly don't need to do all of the stuff that we had to do, but we had to do stuff because there was no machines. Now we've got the machines that takes the load. How much of that do we need to do to get there? And that's open. That's why it's hard being a math teacher, because you don't want to experiment on the kids, and yet you know you've got to prepare them for the world. So it's really very difficult to be a math teacher today. I mean, I only teach college level students, but I struggle with the same issues. Okay, that's rigorous thinking. We could call that pre-rigorous thinking, and then we can call that post-rigorous thinking. And the terminology reflects the fact that most of us in the business think you still have to do some of this to get there. We think you really do have to go through that, but almost certainly not to the extent that we used to have to do. Incidentally, I don't know if there's any people in the audience that are in mathematics departments, pure mathematics departments at colleges or universities. You may think I'm only talking about using mathematics in the world. No, this is how the professional mathematicians in the pure math departments do it. When Andrew Wiles solved Fermat's last theorem, he used that kind of thinking. All professional mathematicians, even if they're working on abstract problems, they almost never use that kind of method. They use that kind of method. They use this kind of method to check the answer afterwards and to write up the results, but that's how they get there. And in fact, the terminology, pre-rigorous, rigorous, and post-rigorous, they're not my terms. There's a very famous Australian mathematician now at UCLA called Terence Tao. He's one of the most famous mathematicians in the world. He's one of the best 4 or 5 alive at the moment. And he wrote a blog a few months ago, maybe a year or so ago, talking about pre-rigorous, rigorous, and post-rigorous, and saying that the goal to be a good mathematician is get over here as quickly as you can. And what I'm saying, which is parallel to that, is the goal to be a good user of mathematical thinking is to get over there. Okay, so now you know how we do it. Whoops, this thing is moving very fast. Okay, go back right now. Okay, you get a recap, okay. Doesn't hurt to see it twice. It's the most important slide on the whole talk, so it's fine to see the recap. Okay, pre-rigorous, post-rigorous. That's the transition we have to get through in education now. That's what mathematics education has to be about. Okay, Terence Tao. Okay, now, the first line of attack, when you have to do the calculations, by do the math, that's an English term that means do the procedural stuff, do the formulaic stuff, solve the equations. But that's the point where we can use Wolfram Alpha. Very easy to use. You just look for the kind of problem you want, and everything on Wolfram Alpha is editable. You'll see little windows with formulas in. You can change that formula. You find a formula that looks like the one you have to solve, and you change the variables. And I'm going to use an example in a minute. Okay. So, going back to this thing, how mathematical models help us understand the world. Okay. And I'm going to finish with an example. And this is an example that I can never give this too many times because it thrills me every time I see it. And this is about understanding exceptionality. Okay. What does it mean to be exceptional? Okay. And we're going to use mathematics. I'm going to use mathematics to prove something that you would maybe like to hear, but you thought was just something that was used to sell some products. We can prove mathematically that every person alive with a very, very small number of exceptionals is exceptional. Everyone's exceptional. You know, people would say everyone is good at something, and it was just something you said to make feel better. Well, now we can prove that everyone's exceptional at something, and it actually has all sorts of implications for the way society should be developing. Okay. Usually for exceptionality, we think of it in this 19th century sort of way of thinking about the bell curve. We think there's a distribution and most people are in the middle, and then at the two ends are the very exceptional. There's the exceptionally good and the exceptionally bad. And so we think of exceptionality, and it's kind of complicated. There's standard deviations, there's all that material about that. And all of that machinery was important in the days when we didn't have computers, but it's much less important now. Okay. So let's make exceptional top 1%. And in order to make the mathematics simpler, I'm not going to distinguish between exceptionally good and exceptionally bad. It just makes it a little bit easier to talk about the two edges. You could do it explicitly for the exceptionally good, but there's no point. It's really about exceptionality. So by exceptional, I just mean very good or very bad. And actually, from the point of view of society, that's really what it's about. If you're a company trying to hire someone, you try to find someone who's exceptionally good. You want to make sure you don't hire someone who's exceptionally bad. And in the middle, there's all these people that, yeah, they may be okay, but you might have to train them a bit. So identifying the exceptionally good and the exceptionally bad is very powerful. So we'll just talk about exceptions. And I'm going to develop a mathematical model, a very simple model, not the bell curve, that talks about exceptionality. It's not about a distribution, it's just about isolating and identifying exceptional people. And maybe you could find another model. This is a simple model that I played around with a few years ago, and I thought, it's another of these cases where I thought I was doing it for the first time, and then other people said, oh, I've been doing this one as well. So, and who knows whether we hear these things or we see them on the web or something. Okay. And this particular model will actually show us that the majority of individuals are exceptional. In the top 1%. Okay, so let's see if we can construct such a model. At this point, we'd better make sure we do it right, because we're going to get a conclusion. I was surprised at the conclusion when I first did it. It's really a dramatic conclusion. But we'd better make sure the model's right, because the model will do some mathematics. That mathematics will give us an answer. It will give us some numbers. To be confident in that, we have to make sure that the mathematics is right. And I'm stressing that because every single one of you has a completely fallacious understanding of volume. You think you understand volume, you absolutely don't, and you'll see why in a minute. Your understanding of volume is completely misguided. The mathematics will tell you why, and you have to live with that. But the good news is it will tell you that everyone's exceptional. Okay, that's what's coming up, and that's the finale. Okay, so we better make sure we set it out accurately, and we better make sure that every step is right, because we're going into territory that the human brain was not evolved to do well. This is way beyond four-dimensional geometry of Tony Robbins and New York City. This is way beyond that. This is multi-dimensional geometry of UPS, FedEx, Amazon, Walmart, etc., etc., etc. Companies that sell thousands of products to thousands or millions of people in many countries, which means they are dealing in geometries of millions of dimensions. And our intuitions about millions of dimensions are hopeless. Okay. This is such a simple model that you'll understand it instantly. And that's why it's a good model. And the mathematics is unrefutable. The only point you might want to argue about is the degree to which it captures what we want. But all I'm looking at is exceptionality. Okay. I'm going to measure exceptionality on an interval. Why not? I don't care about the middle. I don't need a bell curve. There's just everybody else. Then there's the exceptional 1%. So I'll say there's an interval from 0 to 100. And we're going to measure some characteristic x. Anyone who's exceptionally bad will have value 0. Anyone who's exceptionally good at x has value 100, and everybody else is in the middle. That's the model. What more simple model you can get? Because I'm not interested in how people stack up in the middle. I'm just trying to identify the exceptional ones. So I might just as well have an interval, every stuff in the middle, and most people will be in the middle, and there's 1% at each end. Okay? So that's the model. Extremely simple model. So where is the complexity coming from? Why are you about to be surprised? Well, you'll see. Okay. How we get those numbers is irrelevant. They come from something. You know, you can just pull them off the web, you can give people tests, whatever. But you measure them, and you isolate the top one and the better ones. So for one characteristic, there's your model. Exceptionally bad, they're here at the left. Exceptionally good, they're out at the right. And then everybody else is in the middle. Okay. So that's 1% at each end. So the number of exceptional individuals, so that's 2%. 1% at the left, 1% at the right, 2% is the exceptional individuals. And the rest are just normal. That's our model. Okay, that's one measuring. You're measuring one thing. Well, it's very rare in the world that we just want to hire someone because they're good at one thing. We usually want them to be good at more than one thing. So let's measure two things. Okay? Two characteristics. Now I've got an X and a Y, and I've got an interval running from 0 to 100 horizontally, and an interval from 0 to 100 vertically, and everyone is a point inside that. So the exceptional people are the people in the border at the end. They're in the 1% somewhere, because we're measuring two characteristics. Everyone has an X and a Y value. You're exceptional if you're in the top 1% at either end. Okay? And the ordinary people are in the middle. I would expect most people to be in the middle, because our intuitions tell us that if we have nested squares like this, most of the stuff is in the middle. Okay, I mean, this is really just this is like the outside of a box. Well, the number of points altogether is 100 squared. The number of points in the normal area is 99 squared. And so the exceptional people is 10,000 minus 9,604. And I'm old enough to be able to do that one in my head, but it actually was a little bit of a struggle. When I was 16 years old, I could have done it like that. It took me a bit longer. But I'm already at the limit of what I, as a professional mathematician, can do in my head. And it was a struggle. I did it just to see if I could still do it, and I felt good when I did, but it took a lot of time. Okay, 9,604. Subtract it from 10,000, you get 396. So the percentage of exceptional points is that difference divided by the 10,000. So it's no longer 2%. We now have almost 4% of people who are exceptional. You only have to measure two things, and the number of exceptional people has gone from 2% to 4%. That's a sign of hope. If you want to be successful and get a good job, you want to be exceptional. Well, if there are two things involved, your chances have gone up from 2% to 4%. What about 3? Okay, so that was that one. 3.96 as opposed to 2, almost double. Let's go to 3 dimensions. Measure 3 things. Now we're in cubes. Okay, the cube, the outer cube is 100 by 100 by 100. The inner one is 98 by 98 by 98. The volume of the whole cube is 1,000,000. I use the calculator. I just use the simple, cheap, free calculator on the iPhone, and it told me 941,192. I actually did the subtraction in my head as well. Actually, because I've got number sense, I subtracted 10,000 from it, got a negative answer and ignored the negative sign, because I realized that the computer would get screwed, so it was quicker to do it that way. But whatever you do, you use the calculator, 58,808, and then to get the perception, it's almost 6. You've only got to measure 3 things, and 6% of the population are exceptional. We're getting close to being able to develop a company that becomes a world beater because you're doing something that you can do. And I'm going to end with an example of one particular, I'm going to end up with an example of a sports team in the United States that won the championship by using this method. That's one of the, and there's a Hollywood movie about that, and I'll tell you about that at the end. This is a case that's been done time and time again. It is what companies do when they're hiring people. Okay, they make use of this fact. All right, let's go a bit further. What about 10? You know, not difficult to think of 10 things that are important when you're trying to get a job. Now we're in a hypercube of 10 dimensions. Okay. So the volume is 100 to the 10. The volume of the inner one is 98 to the 10. So the outside edge, the exceptional ones, is 100 to the 10 minus 98 to the 10. Your calculator is not going to do that. Or that. The numbers are going to be too big. So you pull out your iPhone, or you pull out whatever you want, or you go to your laptop, and you go to Wolfram Alpha. And it will instantly tell you. So I just found the thing I found an equation that involved just numbers. I found the calculator, and I just edited it and put my formula in, and in an instant it said, here's the exact answer as a fraction, here's what it is as a decimal. I didn't have to ask for this, it gave me that. It says, you probably want one of these, and that was the one I wanted. I could have asked for more, but I didn't. It already gave it to me. Over 18%. You measure 10 characteristics, and almost 20% of people are exceptional when you're measuring 10 things. You've got enough information now to hire a good team to do something. And we'll talk about how you might do that. Okay. But what about really exceptional? What about the 1%ers? Okay. What about 100? If we measure 100 things, what percentage of people are going to be exceptional? Are we going to get close to almost everybody on the planet? Well, we'll find out. Now we're in a 100-dimensional hypercube. Same formula, bigger numbers. Let's stick Wolfram Alpha in. It tells us 86.74% of people in the planet are exceptional. Wow. 100 is not that many. And 200 is 98.24. We're there. We've got the 1%ers. Slightly more than that, because we had to get up to 98 to hit the 1%ers. You measure 200 things, and practically everybody on the planet is exceptional. And just look at how that grew. 200 is not that big. In today's world, it's not difficult to sit down and think of 200 things that are important when you're trying to hire people or build sports teams and things. And you only need to go to 200 if you want to get right down to the top 1%. If you want the top 3 or 4%, it gets easier. These are the real exceptionals. So when grandparents and parents said, don't worry, you are exceptional at something, they would have been absolutely truthful, and now we've got the math that shows that. So let's finish by saying, what have we just learned? First of all, we have learned that our intuitions about geometry are hopeless. Too far. Okay. Because think of what this means. It means if you have a solid box full of stuff, if it's two-dimensionals, if your solid box is full of stuff, most of the stuff is in the middle. With a three-dimensional box, most of the stuff is in the middle. With a 200-dimensional box, a solid box in 200 dimensions, almost everything is on the outside. Everything's exceptional. The middle is empty. 200 dimensions is all you have to go to, so that the middle of a solid rectangular box is empty. It's solid, but it's almost empty, and everything's on the outside. Our intuitions are hopeless, and yet problems that we solve on computers frequently have 200 variables. When you ship a package with UPS, their algorithm uses a lot more than 200 dimensions. And with a small group of high school students in California in January, in 6 hours, those kids in groups of 5 had essentially figured out the algorithm. They'd reverse engineered the algorithm. And I was just their consultant. They had to do it using web resources, trial and error. I gave them some, they did it using just the package one shipping. I shipped a package, kept the record of where it went and when. That was the only data they used. Everything else they pulled off the web, and in 6 hours they'd figured out the algorithm. With me as a consultant. Without me as a consultant, it might have taken them a month. But we did it in 6 hours. But they solved it. Okay. Intuitions are misleading. Now there's the fun stuff. You know, that just tells us how our brain has met its limit there. This really makes it clear that when we say something's exceptional, it really matters what we're measuring. It depends crucially on what you're measuring. If you measure enough things, everyone's exceptional. So almost everyone, and you can take that as many percentages as you want, you can just go to more things, is exceptional in terms of some combination of skills. So this means if you're trying to hire people, you will find exceptional people no matter what things you look for. There will be people who are exceptional. If you are trying to find a job, if you can identify the things you are exceptional at, the combination of talents that makes you unique, if you can find some way of using that, then you can start to be successful. It means a poor country could become a wealthy country by finding out what the population are exceptional at, because they will be exceptional at some combination. Okay? Which means that societies and companies and individuals would be able to lead more satisfying lives if we can make use of the fact that everyone is likely to be exceptional at something. And that's been done. One of the most famous cases was in American baseball. And you can read about this in a book called Moneyball. And this was a club just across the bay from where I live, the Oakland A's. The Oakland A's was a very poor team. They didn't have much money. They couldn't hire good players. If they discovered a good player who did well, one of the rich clubs would hire that player. So they couldn't hire good players, they couldn't keep good players, and because they didn't have good players, they didn't have many viewers, and so they didn't make money to do it. So they were stuck at the bottom, and they couldn't do anything about it, because they didn't have the money to get the audience, to get the money to hire good players. So they were perennial losers. And then they got a coach called Billy Bean, and he brought in someone to change it. He hired a mathematician, Paul de Podesta. And he came in, and he found a team. And he built a team of players, none of whom was an exceptional hitter, none of whom was an exceptional pitcher, none of whom was an exceptional outfielder. These were players that all the clubs were ignoring. But he looked at all of the talents together and said, some of these players, in this range of 10 or whatever it was, I think it tells you in the book how many parameters he looked at. He had many, and it was maybe like 10 or 15. He found players who were exceptional when you measured enough things. And within a year of doing that, they won the competition, the national competition. They won the pennant race. They went from being at the bottom of the league to being at the top because a mathematician came in and said, find people that are exceptional according to this range of characteristics. If you don't want to read the book, you can watch the movie with Brad Pitt in the role of Billy Bean. It's a fun movie. And in the movie, you'll see them talking about how it's done. And they make Paul de Podesta, if I remember right, he looks a little bit nerdy, a little bit tubby and things, but and I don't know whether he really looks like that. But in any case, that's how they did it. So this works. And it's used all the time now. And as I said, this is one of the most uplifting things in the world. It means no country, no group of people needs to remain at the bottom. You can use relatively simple mathematics to identify a suite of parameters in which the people you have in front of you are exceptional and find a way to use those abilities and fit them into the world. That's hopeful. And it also tells us a lot about how societies are structured. We're measuring exceptionality according to a very narrow definition. But in today's world in particular, being exceptional at a range of things is much more important than being exceptional at something. Because if you need someone who's exceptional at one thing, you can hire a consultant. They're expensive. You know, I don't come cheap. But you only need people like me every now and then. But what you need every day is people who have a broad range of skills. And this isn't just me saying that. It's a mathematical result. It's true. Okay, we're done. Okay.
Okay, we have now time for a few questions, but short one, two. So if anyone have a question. Anyone? Okay, I have one. Okay. But if you can be quick. Can you tell us something about your new book, Finding Fibonacci?
Yeah, so that's this book. Just came out in Serbian, the translators in the room somewhere here. This was about a project I did in history. It actually related to this. This was a history into the last big revolution in mathematics, which was the personal computing revolution. Now, you probably think the revolution in personal computing was in Silicon Valley in the 1980s. No, it was in Pisa and Florence in the 13th century. And that was when a guy called Fibonacci, well, that's what we call him today, that wasn't his name, he was called Leonardo of Pisa. He found Hindu-Arabic number system, he picked it up from the Arabic and Persian-speaking traders, he introduced it into the Western world, and just as Steve Jobs, by building the Macintosh, made the personal computer a consumer product, by writing a book that explained in simple terms how anybody could do Hindu-Arabic arithmetic, he made it possible for ordinary people throughout Italy and then the rest of Europe to do arithmetic, to start up a business, to make money, and to do it without any money. You didn't need money to learn how to do Hindu-Arabic arithmetic, and when you did that, you could create a business. As a result of that being in Italy, in Pisa, in the 13th century, coming out of Pisa in Italy in the 13th century, we have Pisa and Florence, we have double entry bookkeeping, we have banking, we have insurance, we have the beginnings of international trading empires. All of that happened within a few decades of Hindu-Arabic arithmetic coming into Western Europe, and it happened because ordinary people could learn how to do arithmetic, and when they had that ability, they could compete with the big guys and create powerful companies and powerful conglomerates. Just like in Silicon Valley, when personal computers allowed fast digital computing to be available to everybody, thousands of young kids became millionaires because in a few years they could make successful companies because it made it democratic. The tools became available to everybody. So I actually thought that was interesting, especially coming from Silicon Valley, and especially because Fibonacci was a very famous popularizer of mathematics. He did what I like to do, which is to make it available to everybody. I was interested in him. I spent several years researching him, going to Italy and talking to scholars, going to the archives. In 2011, I wrote a book about his life, which was called The Man of Numbers, and that was a history book. But the process I went through to find out about it and the people that I met was so interesting that I took all of my notes and wrote another book, which is my personal journey to find out about Fibonacci. And there were several very interesting characters along the way. And it was my attempt to go into the archives and figure it out. And it was such an interesting story that I actually, for the first time in my life, wrote a book that was semi-autobiographical about that process. So it's a bit of a travelogue, it's a bit of a history, it's a bit about changing the world with science. There's a bit of a comparison between Silicon Valley and 13th century Italy. It's a book that's really sort of all sorts of things, which means it's non-technical, it's readable, and if you buy it, I hope you enjoy it. And you can read it in Serbian now.